All right, let's talk about what happens to mass and momentum when we start traveling really fast. So I've got Sally, she's on the ground, and I've got Bob in a spaceship moving very fast in this direction. And they both have identical balls, and both balls are thrown at the same speed as measured by the person who throws them. So according to Bob, he throws his ball at whatever, let's say 5 meters per second, and according to Sally, she throws her ball at 5 meters per second. So, what does Bob see? He sees his ball normal speed, yes? And when Sally looks at her ball, she sees her ball at normal speed because those balls are in their frame of reference. Everything's fine. Now, when Bob looks at Sally's ball, because of time dilation, if Bob was looking at Sally's clock, he would see it moving much faster. If she had a clock, let's say, right here, he would see it moving faster. So when he sees her ball move, he sees her ball moving fast. And the same idea when Sally looks up at Bob's ball, or when she looks up at his clock, she sees it moving slowly. So therefore, when she looks up and sees his ball, she sees it moving slowly. So she sees his ball moving slow. Okay? So when they hit, they move off with the same speed. Because keep in mind, they had the same mass, and they have the same initial velocity. So when they hit, they should move off with the same speed. Okay. Except, okay, yeah, same speed, not the same velocity because the direction is definitely changing, but the same speed. So momentum will be conserved according to the theories of relativity. Momentum will be conserved from Bob's frame of reference and from Sally's frame of reference. So just scroll a bit. So if we have if V is slower, whoa, lost. Yes, and that's when Sally looks at Bob. For them to have move off with the same speed, then Bob's mass of ball must be larger. So let me repeat that. Momentum is conserved. When Sally's looking at Bob's ball, she sees it moving slower. Now, if her ball bounces off at the exact same speed, she's saying, well, his ball's got to be bigger, right? Because P equals mv. She sees this thing as smaller. She knows their momentums must be the same because her ball bounced off exactly the same. Didn't bounce off slower after it hit his ball. It didn't bounce off faster. So everything about it hit the momentum of his ball must be equal to the momentum of hers. That's what she realizes. So if V gets smaller, M must get bigger. So conversely, if V is larger, and that's when Bob looks at Sally, yes, then Sally's ball must be, let's say, lighter. Yes? Because again, she sees this as bigger. I apologize. He sees this as bigger, so M must be smaller. Because again, his ball bounced off identically when it hit her ball, so he says, oh, our momentums must be exactly the same, so this must be a constant, and if one goes down, the other one goes up, and if one goes up, then the other one goes down. The net result here is that, yes, mass changes. And it changes according to this formula right here. We have the rest mass, we have the relativistic mass, we have this factor right here. Some other quantities that are going to be affected when the mass changes is momentum is going to be affected. Momentum used to be mv, but now because m is changing, I get this version of the formula. We learned in grade 8 that the energy of something, of an object, is equal to mc squared, but the mass is going to change, so when something is moving really fast, its total energy is going to change. The total energy of an object that's moving is now mc squared over square root of 1 minus v squared over c squared. And if it's moving, it's got kinetic energy, and if you're asked to calculate kinetic energy, I could take the total mass and I could subtract the rest mass, and I could figure out how much kinetic energy this object had. So here, that's our brief look at mass change. When something starts traveling really fast, it changes according to this equation here. How I came to this equation exactly, I don't care. I just decided that I would give you this little thought experiment here of the two balls bouncing and momentum being conserved.